It's a pleasure and honor to speak here. I think I first met John Pierre in the early 90s at a conference at Johns Hopkins. I think he was talking about Fujita conjectures. And throughout my career, I learned from him about things like multiply ideal, vanishing theorem, and Saussure constant. Those all have important influence on me. And anyway, I take this occasion to say happy birthday. All right. So I just want to talk about something fairly simple that is about computing discrepancy of the relative canonical divisor and how it related to dimensional secant varieties. So the motivation is come from the joint work with Mary, the poor, myself, Isocel, and Brewery. So the kind of question we were studying is the following. So you're starting out of X, let's say irreducible projective variety. Of dimension n. And well, we know that the X is rational. That's the same thing as saying that there is a rational map. Yeah, a rational map of degree 1. Yeah. And in general, one can define so-called irrationality of X. We define to be the minimum of all the finite, generic finite map. Where phi is one of these map QPN, is generic finite. So this is clearly a birational invariant by definition, almost. And so in the case of special case when X is a smooth projective curve, this is just a classical gonality of X. Yeah. Go on. So it's just asking what is the lowest degree. X can be expressed as a ramified cover of P1. Now, I mean, such an invariant probably in general probably very difficult to compute, but there are some examples one can compute, and that's what we did. And so I think, so the theorem like this. Let X be a very general surface degree D, Pn plus 1, so dimension of Xn, and D is greater than or equal to 2n plus 1. Then the irrationality of X is equal to D minus 1, and they are basically just given by projecting from a point on the hypersurface to Pn. And I mean, the question, of course, becomes very tricky as you decreasing d, because even we don't know whether cubic free folds are all rational or not. So, right. And I mean, I should remark some more historical remark that when n equal to 1, so this is a plane curve, and this is a theorem of Noether. And n equal to 2 and 3. This is earlier result of Bassanelli. And now, the idea of proof is fairly simple. So you let f be one of this map to Pn, compute the irrationality of x, that's the degree of f equal to delta. And so we know delta is less than or equal to d minus 1. And we know the canonical bundle of x is d of minus n minus 2 by junction. From the canonical bundle, that's not hard to prove that a curve through a general point has gonality at least d minus n. And from that, you can deduce that this number is between d minus n and d minus 1. Okay. Oh. See? This one? Now, to make observation due to corolla is the following. So you have this map X. It may not be a morphism, but you can resolve this morphism. So making this a birational map, and this is become a morphism. Then since this is smooth, we see the n form of x is the same thing as the n form of x tilde. On x tilde, we have the trace. But of course, the projective space has no n form, so this is 0. So therefore, the trace map on n form is 0. What that implies is the following. If you take P in here, a general point, equals P, I call this CP, a zero-dimensional scheme. This is just delta point. Satisfy so-called Cayley-Buckler property with respect to omega x. Well, just because the trace is 0, so if you have something vanished on delta minus 1 point, since the sum is equal to 0, therefore it will vanish also at the last point, and this is a so-called Cayley-Buckler property. Now, one of the classical projective geometry lemma is the following. let's say you have m distinct points. And let's say you satisfy Cayley-Barker property. With respect to OPN of K. Then that implies, for instance, that one, the number of points is greater than K plus 2. And 2, if the M less than equal to 2K plus 1, then that implies that this thing are collinear, lying on the line. So apply this to our situation with delta point, and we know the linear system we're dealing with is d minus n minus 2. A simple arithmetic say that this property applies. So that implies that Q1 to Q delta CP taking the line. Yeah? So what this means is that then this map F would determine an n-dimensional family of lines coming from this morphism. So this determines a variety of dimension n. So F variety, that's a B bar inside the Grassmann of line in Pn plus 1. And we can resolve this, resolve the singularity. Resolution singularity. And over here, you have the universal family of line, and then you can pull back this to a universal family of line over B. So this is B. So this is n dimension, this is n plus 1 dimension, and this determines the map back to Pn plus 1. This offers this generic finite Q1, and with a little bit of work, you can even prove that this is a birational map. And now I look at the inverse image of the divisor X. Then this now becomes a divisor in W. W is this universal family of lines. And this is equal to the proper transform of X plus something else, exceptional divisor. And you can write this D into two parts, that's like E plus F. E are all the components of D that dominate B. B is this family of lines. And that's why E this part to be AI. Now, so you have this map from W, B to B. This is the universal family of line. You take a line, a class of line here, look at the pullback. So this would be just a line. You can regard this as close-up, just a subvariety of a line inside the projective space. And now I want to compute the relative canonical divisor. That's where the discrepancy coming from. And I want to restrict this to the line. Well, the normal bundle of this line in W is trivial, so the canonical bundle restrict to the line is just OP1 and minus 2 by adjunction formula. And we know, so Pn, sorry, and Kpn plus 1 restrict to the line is just minus n minus 2. And altogether, you see that this is just OP1 of n. Now, you take one of these component EI coming from the inverse image of X, and under the map mu, this go to some subvariety S. Let's say dimension of S to the small s. So a simple calculation of the ramification, just because this thing had codimension n plus s plus 1 in the projective space, one can see that order of I is greater or equal to n minus s. Do this calculation more carefully later on when compute dimensional secant variety. And together with intersection number, so we see the n, let E be the degree of the map from E I to B. And we know that the summation, because the delta is between d minus 1 and d minus n, the lower bound d minus n tell you that summation ai, ei, dot the line is equal to n. Less than equal to n, since this is less than equal to sign. And together with this, that means this implies E times n minus s. This is the sorry. That's right. And let me just say that this altogether implies this degree of this thing times n minus s is less than equal to minus s is less than equal to n, or E, this degree of this map is less than equal to n over n minus s. Now, put this together, you see you have this EI V. This is a rational variety. So that means the irrationality of EI is less than or equal to E. Now, you take a rational curve here, putting it back to here, then you get a curve of gonality at most E. And this curve pushed down back to S will give you another curve that has gonality bounded by also E. Now, an old theorem of Marcel and Voisin that tell us that we can understand the canonical divisor of S of a resolution of S, and we know that there is a resolution here. There exists a resolution such that Ks tilde is of the form G upper star of S. So this is somehow measure how, in some sense, how genotype the generic hypersurface is. But in fact, you can sort of measure such that this subvariety is not only of genotype, but you can measure how big the canonical divisor is. So plus the effective divisor. And this implies that the gonality of the curve for a general point of S is greater than d minus 2n plus S. And put this together, you find together, and this implies that d minus 2n plus S is less than or equal to n over n minus S, or d minus 2n S. And S is between. Now, if S is zero-dimensional, that will mean that the divisor contracts to one point, and that means all the lines will be also through one point, and then this will tell you the map will be given by projection through one point on the hypersurface. So we can exclude the case that S is dimension 0. And in that case, then that implies this number is less than or equal to 1 by simple estimate. And therefore, D is less than or equal to 2n plus 1. So if D is bigger than 2n plus 2, we get a contradiction. The case D equal to 2n plus 1 require a little bit more argument. Let me ignore that. All right. Anyway, basically, this is how reduced response of line in how they intersect the variety. So let me talk about secant variety a little bit. So the classical theorem is saying that if you have a curve, a smooth projective curve, Pn, then the so-called trisecant lemma for curve is saying that, for space curve, is saying that you look at considered order line, so L intersects C, the length is at least 3. then the union of all these curves with a closure. Then the dimension of this thing, this is so-called this trisecant variety. And we know the classical result is in dimension of this trisecant variety is less than or equal to 2. Since we know there are the secant variety should be three-dimensional, and so therefore that tells you a general secant line is not a trisecant line. And this had been generalized by Sifran in the early 90s. So let me set this up a little bit more generally. So let X this time now instead smooth. Let's say you have irreducible projective variety. Again. And I consider those lines. L such that 1, the length of L intersect X is greater or equal to K. And 2, the L intersect X is sitting inside the smooth part of X. Let me call this star. Then I look at the union of all this line. Take its closure. And let's call this Sk of X. This is the K secant variety of X. Of course, if X is smooth, then this doesn't matter. Now, in the early 90s, maybe 91 or 92, Sifran generalized the classical trisecant lemma, and to prove that dimension of Sn plus 2, X is dimension of X equal to n, is less than or equal to n plus 1. So in the case the X is equal curve n equal to 1, this is precisely the trisecant variety. And you're saying that the union of all the trisecant is two-dimensional. So this generalizes the classical trisecant lemma. A few years ago, Eisenbert and Behesti and Eisenbert generalize the Sifran formula to for any k. This is less than n plus 1 plus n k plus 1. So again, if you set k equal to n plus 2, you recover this formula, where this is the integer part function. And so anyway, so this is now it turned out that this kind of formula is worked much more generally. So for instance, you can get the following thing. For instance, you look at smooth curve of degree d. And genus G, and you can ask how much this curve can intersect the variety. Again, you look at to see this curve. and X. And then the dimension of T. So you can look at the union of all the C to say this is star. G, X, and then the dimension of this thing. That's something like 1 plus. Let's see. And plus 2 degree of C 2G minus 2 over G minus degree of C. So anyway, if you set degree of C equal to 1, genus equal to 0, you recover the old formula. And similarly, you can do this not just with line, you can also do it with linear spaces. As long as linear spaces intersect X is a hypersurface, then you can do a similar kind of estimate. So let me ignore that for a moment. Now, the proof of this sort of thing is rather trivial. So let me try to prove this. Perhaps the Eisenberg. Okay. Now, so suppose that this is false. So assume that. Let me let T to be this number. Now, by taking generic projection, you can project X project X to Pn 2. This is n plus T plus 1. And you can reduce to the case that X is sitting inside this projected space, and the dimension and the secant variety equal to the n-field projected space. Just because generic projection of a line is a line, if X intersects X is in the smooth part, then a generic projection also preserves this property. Right? So we reduce to this case. And then just like before, you can take a n plus t dimensional family of line inside a Grassmann. I mean, again, this may be singular. Let me resolve the singularity. So I can reduce to this is smooth. Yeah. And just like before, you have this family of line, WB. Lines, universal family of line. map mu again. And again, you do the same thing. You compute the relative canonical divisor. This may not be a birational map, but it's still a generic finite map. That's good enough. See that this is just like before. Plus t plus n plus t. And again, I look at the inverse image of x, the ideal of x dot OW. And this thing split into a divisorial part. You know that each of the x will intersect each of the line at finite number at k point. So this is a device, certainly have a divisorial part, but may have some high codimension part also, but doesn't matter. So this is equal to so minus d. Then there's some ideal. And just like before, you split this d into two pieces, just like before, plus f. So E are the components dominating B. So these are the things that my finite Q1 to generic finite Q1 to B, and so and the E equal to 6 AI. Now, this means the order, generic vanishing order of EI of the ideal shift X is AI. Yeah. You don't. This is not birational here. This is certainly not, in general, not. But there are examples. This is really high degree. In the before, you birational, but here, really, there are examples really high degree. Yeah. Now, again, I want to compute the order of EI along EI. Okay. Well, the image of EI would be some S. And let me, for simplicity, for S, let's say, is equal to X. If it's smaller than X, the inequality will be in your favor. So let me just assume this is the case. Now, locally, the choose coordinate so x1 up to t plus 1 in Pn, and leave some other thing. And this is coordinate in Pn near at a point at a general point in X. Now, and then EI, let's say upstairs coordinate at the general point. EI. Let's say C1 equal to 0, define EI. And then we have C1 and plus 1. The coordinate upstairs. And now using the order of vanishing is AI of IX. So what that means is that you can write xi is equal to ci to the ai times some other element u, ui. May or may not be a unit. This is true for I equal 1, t plus 1. And now you look at dxi, then this is ai minus 1, ci u plus I. And you look at the wedge product. And since dc1, where dc1 is equal to 0, then you see that this expression will be equal to c1 to the t plus 1 ai minus 1 times something. And so this implies that the order of kw pm plus 1 greater than equal to t plus 1 ai minus 1. And since ai is greater than 1, so this is bigger than tai. And on the other hand, we know that the line, the length is at least k. So you know that summation tai summation ai dot l is greater than equal to k. So put this together, and we find t times k is less than or equal to n plus t. This is, remember, this is the kw. It's 1. And we find that p is less than or equal to n over k minus 1. But remember, t is equal to 1 plus n over k minus 1. And we get a contradiction here. So, and this is the proof. Okay. Yeah. So, I mean, this sort of theorem is related to things about generic projection, and for instance, there is this conjecture of Eisenberg and Gorto about effective cell vanishing theorem for ideal shape of variety. So the conjecture there is saying that let me just state the conjecture. Let me just say it for the smooth case, that the general case of conjecture turned out to be false by recent work of McCullough and Pever. let me just state this for smooth variety. So if X a non-degenerate smooth variety, of dimension n, Pn, let E be the codimension X, then they predict the following vanishing theorem for the ideal sheaf. D minus E plus 1 minus I plus n 0 for I positive and 0. So this is basically it's an effective version of self-vanishing theorem, only depend on the degree of the variety. And for low dimension, the dimension x equal to 1 and 2, this conjecture is true. And the proof very much depends on this sort of generic projection. You need to avoid certain type of secant lines. And in dimension 3, then the conjecture is proved by Cifran for if n is bigger equal to 9, and by Quark, you see that you can off by 1 in the 3-fold case, and the 4-fold case is off by 2, again, by consideration of generic projection. So let me just stop here.